will be on DC motor characteristics. Most of the DC motors you will work with are technically called permanent magnet DC motors. There's simply two wires. There are simply two wires for the motor. These connect through brushes and the commutator to provide the current for the motor. The permanent magnet provides the field. Together, the current and the field will create a force through the F equals BIL equation. Here are a couple DC permanent magnet motors. Here's a simple one that is used for a volume control on a stereo system, a DC motor used for a small scooter, and a little DC motor used for a drive mechanism. First, we'll take a look at the standard DC motor, the one for the scooter here. We'll apply a voltage through a power supply. And as we see, as we apply the voltage and increase the voltage, the motor spins. Two wires are all that is needed connected to the motor. The permanent magnet, though, is inside. If the speed that is running that voltage is too large, we normally use a gear motor or gear reduction. This motor has a gear reduction, still a two-wire permanent magnet motor, but as I apply the voltage, I get a much slower speed, something that would be typical of a robotic system. The large metal piece between the motor and the rubber drive is the gear reduction motor mechanism. If you need even more reduction, you can use a multi-stage gear drive. We'll adjust this up, and you can see very minimal slow speed. If you take apart these mechanisms, these small DC motors, here we have a gear train system that connect to the motor. The motor is in a shaft. To connect to the winding on the shaft, the red wires we see here, we use a brush commutator setup. There's the brushes, and the commutator is on the back end of the motor there. And then we connect into the motor through the external connections. If I place the conductor or the rotor inside, you can see it is pulled in by the permanent magnet. So the permanent magnet is the magnetic section right inside of the motor there, the little gray piece. And of course, when I attach the motor, it pulls right in. So this is going to rotate inside of that magnetic field. Current will flow in the windings, the red wires there, and that will create the current. The magnetic field produces the B field, and we will get a force developed to create the acceleration and eventually the speed of the motor. Permanent magnet motors are generally smaller, sub-horsepower motors. And so the easier motor we have to test is called a shunt motor. Now the shunt motor has the field winding to produce the magnetic field, as we see in this diagram. It's called a shunt motor because the field is in parallel with the armature section, which is the brush and commutator section. So the applied motor voltage provides current for the field, which creates the magnetic field B, and also for the motor current. The force is BIL, B from the field, I from the armature current. So this is the motor we will be testing today. Now in this setup, we will separate out the field and supply it with a fixed 120 volt DC voltage. The armature will be supplied by a separate power supply, and this allows us to look strictly at the motor current for the I in the F equals BIL equation. The B will be fixed from this supply. So with this setup, as the current changes in the motor, we'll get a varying force out. In reality, the motor load is what determines typically the current flow in the motor. In order to get a current into the motor, you need to have a load applied to the motor. We will apply a load through the electrodynamometer. So the DC motor we will look at today is called a separately excited DC motor, in that the field is excited by its own power supply. In this case, 120 volts DC will supply the field winding. The armature, which supplies the current to the conductors that are rotating, the armature, we will refer to this, is supplied by its own power supply through the brushes and the commutator to the conductor. The motor is shaft coupled through a belt to an electrodynamometer. An electrodynamometer is a method by which we can apply a load or torque to the motor shaft. As the motor torque or load torque is increased, the input current to the motor will change. So and the speed also. So the motor speed and current is dependent on the load. We will vary the load through the 120 volt control on the electrodynamometer. That will produce a torque which the motor will need to balance, and it balances it by slowing down and also increasing the current into the motor. Current times the current in the BIL equation creates a force, which then works to counteract the applied torque. Motor action, of course, is F equals BIL, B from the field, I from the current. Force becomes a torque. Torque accelerates the motor to a given velocity that will balance the torque applied through the load. Now, the characteristics that we will be looking for is the motor's torque and speed characteristic. This graph shows the load torque on the horizontal axis, the motor speed in the red line, and the motor current in the green line. As the load torque is increased, the motor will slow down and the input current will increase to provide the power to provide the load torque. This is the setup we will be using. The power supply will supply both the variable or the armature current voltage and current, and the supply below it, the shunt field. This is the DC machine. It can be a motor or a generator. We have the armature current here and the field current here. Initially, we will start with the motor by itself, not coupled to the electrodynamometer to see the power requirement just to spin the motor. We will measure the speed of the motor and the torque out of the motor. We also measure the current into the motor and the voltage applied to the motor. So, initial startup, voltage applied to the motor provides current through the windings and also the commutator brush setup to get the current on the rotating section. Force equals BIL, torque provides the speed. The motor current is 0.26 amps, and the motor voltage in this case is 158.2 volts DC. The speed is read by the laser tachometer. Now I'll see if we can get a good reading here. So a value around 1600. There's the laser pointing at a piece of reflective tape. It's a little variable. So the speed of the motor in this case is around 1700 RPM. 1709 is the steady reading there. Now we have coupled the motor to the dynamometer, the electrodynamometer. Now we have coupled the DC motor to the electrodynamometer through a belt. We will read the torque developed in the electrodynamometer in the bottom scale, which is below the rotating shaft of the electrodynamometer. When we energize, we see a torque is developed on the electrodynamometer. In this case, about 0.8 pounds/inches, or about 0.8 inch-pounds of torque. The speed will have also changed because we have now loaded the motor. In this case, the speed has reduced to 1626 RPM.